Hello, friends. Welcome to lesson 311, where we're going to be learning about another um, set of trigonometric functions, but they're related to sine, cosine, and tangent. So they're not really like totally new. They are they're based on sine, cosine, and tangent, similar to the way the inverse functions were. These, though, instead of being inverse functions, they're actually what we call reciprocal functions. Okay, so you can see the first one here, secant. Secant is equal to 1 over cosine of x. It's just that these functions, they get enough usage that they get turned into their own function. They get their own name. And so secant is the reciprocal of cosine. Cosecant, so we abbreviate that CSC, just like we have, sine is SIN and then cosine COS, right? So we have different ways of uh, abbreviating these different things, all because we're lazy and we keep it as brief as possible. That's really all of this stuff, right? It's just code so that we can write as little as possible. That's why in math, if there's something there, you got to pay attention to details. If there's something there, it's there for a reason. We don't write extra stuff just for fun. It's an exercise in laziness. It's putting it crassly, of course. But so anyway, and cotangent is 1 over tangent. And since tangent is sine over cosine, then cotangent is cosine over sine, right? Again, as long as sine of x and tangent of x, as long as don't equal 0. So what do the graphs of these look like? Well, if we take a look at secant, right? Secant is 1 over cosine. So you'll notice that in here, this is the cosine function, and then 1 over that. Well, this is just 1 over 1. And so it's 1. But as cosine gets closer to pi over 2, as x gets closer to pi over 2, cosine gets smaller and smaller. So that means 1 over cosine is going to be getting bigger and bigger. And then at the value pi over 2 and at 3 pi over 2, etc., the places where cosine equals 0, we have an asymptote there. So we get asymptotes for secant at the places where cosine equals 0, which makes sense, right? And it works the same kind of way for cosecant and sine, right? At sine of 0 is 0, but 1 over 0, you can't have that, so, right? So that's an asymptote there. Also at pi, at 2 pi, etc. All right, and so the thing to notice is that the domains for these functions are all the places, basically everything except the places where, in the case of this one, cosecant, uh, all the places except the places where sine of a function equals 0. Notice the range, there's nothing in the middle here, right? And so the range is from negative infinity to 1 and from 1 to infinity, right? The domain is this, the range is the vertical, right? Horizontal is domain, range is the vertical. The outputs are restricted to being less than -1 or greater than +1 for both secant and cosecant. For cotangent, um, similar kind of thing here, right? Realize that the original tangent graph looks something like, let me draw it, something like this, right? Where it's kind of crossing at the 0, pi, etc. But then notice now it's these places where tangent is 0 that we have our new asymptotes, because 1 over tangent, 1 over 0 would give you an asymptote at those places. So let's look at some examples, right? Let's start to try to work this out. First one, let f of x equals 3 secant of 2x, which of the following is a vertical asymptote of the graph of f. So secant is 1 over cosine, right? And so I'm going to have an asymptote, secant of 2x. This is equal to 1 over cosine of 2x. I recommend just writing this out. Just write what it equals, in terms of sine, cosine, and tangent, so that you can see. So I'm going to have an asymptote at the place where cosine of 2x equals 0. Right now on the standard cosine graph, that's just, cosine of theta. The standard cosine graph, I have asymptotes at pi over 2, right? So when 2 of x equals pi over 2, that's when I would have an asymptote. So that's here when x equals pi over 4. And that's option C. Next one, 4 minus 2 cosecant of pi x. Which of the following is a vertical asymptote of g? Okay, so again, cosecant. By the way, what does the 4 do in there? If we have this 4 here, that's just shifting the midline, right? And then the -2, that's changing kind of the amplitude, you could say, and flipping the whole thing, the graph, of course. But in terms of where the asymptotes are going to be, that's what concerns us in here. So let's focus in for a second. So cosecant of pi x, that's equal to 1 over sine of pi x. Now, again, so sine, the standard sine graph equals 0 when theta, or x, is equal to 0 and pi and 2 pi, etc. So basically the multiples of pi. And so the places where I'm going to set pi x equal to pi. And so here I just end up with that x equals 1, where x equals any integer value, right? So that's going to be D. All right, so now we've got function h, 3 cosecant of theta over 2, which of the following is the range of h. So again, the range is the output, the y output. When it's just plain secant or a cosecant, then the range is, more than 1 and less than -1. But this 3 in here, what that's doing is we can think of it as changing the amplitude of the function. Okay. uh, again, when we've got something outside being multiplied, that's like a vertical dilation. And so the whole thing is being shifted, right? Stretched. And so the answer is going to be from -infinity to -3, and then from 3 to infinity. Right. Okay. And then 4. So k equals -5 cotangent of 2 pi x. Which of the following is a vertical asymptote of the graph of k? Okay, so cotangent is, so if I have cotangent of 2 pi x, I'm going to ignore the -5 because that's just doing things vertically. I'm just looking for where the asymptotes are, so that's only what's inside the function. So this is equal to 1 over tangent of 2 pi x. So I'm looking for the places where tangent is 0. The places where tangent is 0 are at the places where cosine is 0. So that's at pi over 2, 3 pi over 2, etc. So that's when 2 pi x equal, sorry, where sine equals 0. So that's at, right, make sure 0, pi, etc. So when 2 pi x equals pi, and then any multiple of pi. And so x is going to be 1/2. So at the value 1/2, that's where there's going to be an asymptote of cotangent of 2 pi x. Okay, continuing to apply what we know here and apply, we can, just like we can answer questions about asymptotes and zeros and maxima and minima and all those types of things, we can also solve these things the same way we did before. Okay, so again, the general approach is get your equation together, isolate the trig function, and then in this case, take that extra step of putting it in relation to sine, cosine, tangent, and then think about it in terms of sine, cosine, and tangent. So in this place, we're going to find the intersection of these two graphs, these two functions, f and g. So I'm going to, and we're restricting ourselves to the domain of 0 to 2 pi, including 0, not including 2 pi. Okay, so this is going to be 4 cosecant of x plus 3. I want to know the places where this is equal to 11. So 4 cosecant of x equals 11 minus 3 is 8. Divide by 2. So cosecant of x equals 2, right? 8 divided by 4 is 2. And so what we're saying here is I'm looking for the place where 1 over sine of x equals 2. Now, what do I do at this point? Well, we're trying to solve for sine of x. With the place where 1 over sine of x equals 2, is the same place where sine of x would equal 1/2. So you can think of it as multiplying the sine of x to the other side, bring the 2 down underneath. So 1/2 equals sine of x. So this is going to be the place where sine of x equals 1/2. So on my unit circle, sine is the vertical, 1/2 is the smallest of these two. And so this is going to be at pi over 6 and 5 pi over 6. Right? So x equals pi over 6, 5 pi over 6. Again, same thing we were doing before. Put in the regular sine, cosine, tangent, and then you have to solve a little bit more. And then it's the same as what we've done before. Right. Notice the way that math works is like we get this one new idea, and then we try it out with all the other things we had done before and see how it fits in, how it all kind of ties together. So, example 6, let's take a look here. I want to know, again, points of intersection from 0 to 2 pi. And so this is going to be, set them equal to each other, 3 minus 1/2 secant of x equals 4. So I'm going to subtract 3 from both sides. I get negative 1/2 secant of x equals 1. I'm going to multiply negative 2 to both sides. So the place where secant of x equals negative 2. Okay. Secant is cosine. So one place where 1 over cosine of x equals negative 2. And so I'm looking for the place where cosine of x is negative 1/2. On my unit circle, x is the, um, the horizontal coordinate. And I'm looking for the places where it's negative. So that would be here and here, these two places. So this is 2 pi over 3. And this would be 4 pi over 3. Okay. I'm restricted in my domain, so I'm not going beyond that, like plus 2 pi k or anything like that. So x equals 2 pi over 3 and 4 pi over 3. For example 7, they want us to use a calculator because it's got some decimal numbers in it. And so I'm going to go to Desmos, and basically we'll put in this function p, and they want to know where does this equal to. So then what I do is I put in the value y equals 2. I just put in that, and I look for the places where it intersects. It's really easy in the Desmos function calculator. Let's take a look. Okay, so in the calculator, I put in the function that I have there, and I put in this function, that just y equals 2. And in my domain, right, 0 to 2 pi. So if I'm looking in terms of numbers, that's roughly from like 0 to about 6.2. And I can see that there's this point right here. I just clicked on it, and it gives me the value 4.07814. Okay, we like to go to 3 decimal places, 4.078 or 4.0781. And that gives you the solution to this. Again, it's really simple in the calculator. You just put them both in there and you look for the points of intersection. You can just click on them and it gives you the coordinates. So that's it. That's the last example for this lesson. Thanks for watching. Don't forget to like and subscribe.